Think about what it takes to power a modern city. Every time you flip a light switch, turn on a tap, or catch a train, you are relying on a massive, invisible web of physical machinery constantly working in the background. We call this system Critical National Infrastructure, or CNI. You can think of it as the physical muscle of our society. It does all the heavy lifting required to keep the economy running and the public safe. A major part of this muscle is the energy sector. Power generation and electricity transmission are the lifeblood that keeps everything else moving. Then there is our water supply and treatment. These massive facilities run continuously to filter and pump clean water to millions of homes and businesses every single day. Because we rely heavily on these physical muscles for our daily survival, any disruption to them causes immediate problems. A failure here becomes a direct threat to national security and public safety. But all that heavy machinery cannot run on its own. To operate at such a massive scale, it requires a highly synchronized control system to tell it what to do. That brings us to SCADA, which stands for Supervisory Control and Data Acquisition. If the infrastructure is the muscle, SCADA is the digital brain. It allows operators to monitor and direct vast industrial processes from a central room. The brain communicates with the muscle using specific hardware components called PLCs, or programmable logic controllers. These small boxes sit between the digital and physical worlds, translating computer commands into real-world actions, like opening a water valve or speeding up a turbine. Down on the factory floor, operators use a touchscreen called an HMI, a human-machine interface, to safely adjust the physical settings of the machinery. This creates a clear reality. Whoever controls the digital SCADA brain possesses total control over the physical muscle of our society. To understand how these systems come under threat, we have to look at how businesses are structured. There is a divide between information technology, or IT, the computers in the corporate office, and operational technology, or OT, the machines doing the physical work. This diagram shows the specific path a cyber attack takes. A digital assault almost never starts at the factory itself. Instead, it usually begins in the corporate IT network, often through a standard vulnerability like a phishing email opened by an office worker. Once inside, the attacker quietly creeps through the office network. They map out the computers and servers, searching for a pathway that leads to the critical machinery. Then comes the pivot. The attacker crosses the poorly guarded digital bridge separating the office computers from the industrial SCADA network, reaching the central control servers. Now inside the operational network, the attacker takes control. They can alter the logic inside those PLCs, send malicious commands to sabotage the physical machinery, and even suppress the warning alarms so the operators have no idea anything is wrong. Because modern businesses want the efficiency of managing their factories from their office networks, they have inadvertently built a bridge. That connection allows digital threats in an office to cause physical damage to industrial equipment. You might wonder why the SCADA brain is so easily tricked. The answer is that many of these industrial setups are legacy systems. They were originally built decades ago to be highly reliable, but they were not built for internet security. To communicate, these machines use specialized industrial protocols like Modbus or DNT3. You can think of these protocols as old languages that the equipment uses to talk to each other. This animation shows the problem with these old languages. Because they were designed long before cyber attacks existed, they often operate in plain text. They don't require passwords and lack encryption, meaning the data can be easily intercepted. Without a way to verify who is actually sending a command, the PLCs will blindly follow whatever instructions they receive. They simply assume that any signal traveling on their internal network is friendly. Defending these environments requires recognizing a hard truth. The machines cannot defend themselves. Their core design assumes a level of trust that no longer exists in the modern world. This vulnerability has a real-world cost. When a ransomware attack hit the IT network of a massive fuel pipeline operator, they had to shut down their physical operations to stop the infection from spreading, causing widespread fuel shortages and panic. The primary cure is strict network segmentation, rebuilding the walls between the IT and OT networks to block threats. Inside the protected network, passive monitoring acts like a radar, safely scanning the brain's signals for anomalies without interrupting physical operations. But technological walls must be paired with human vigilance. Rigorous staff training, and careful checks on software suppliers are required to stop the initial breach from ever taking hold in the corporate office. The digital brains controlling our world face constant threats, but by properly separating those networks and guarding the pathways between them, we can ensure the physical muscles of our society never stop moving.